My name is Peter Bøgel. I work at the physics department at the Technical University of Denmark. I will now show you some examples of digital experiments that we are working on. These are small programs running in HTML and JavaScript and are compatible with nearly every browser, even browsers on phones. The purpose of these digital experiments is to make teaching more engaging, experience-based, and interesting, and maybe even better. It is up to you to judge whether this is useful or relevant for you. We think it's very cool. Enjoy. I will now take you through some of the DEX, some of the digital experiments we made. One of the first ones was this gas simulator, where you can change the temperature, and which is corresponding to the kinetic energy of the particles, and you can see how, if I speed the particles up, I can see that the velocity distribution and the collisions per second are changing. So let me stop this. And here's another simulation that simulates chemical vapor deposition growth of graphene. So you can change the partial pressures of methane and hydrogen and temperature, and even the activation barriers for diffusion and dissociation, and so on. So it can increase the hydrogen partial pressure, and you can see that the etching rate increases dramatically. There's still some bugs in it. You still get these gaps here, but more or less it contains a lot of what we know about CVD growth. You can also have different orientation of these domains, which gives you these kind of irregular grain boundaries. There are some presets here. Low temperature growth, where the growth is very slow. So you can see here, I would need to increase the temperature a bit here to get things going here, so I can see how the growth rate scales with the temperature and so on. This is a transmission electron microscopy image lab, where I can learn how different crystal structures they may look. This is graphene in this particular case, depending on the defocus, where the object model is seen down here, and you have the diffraction patterns to the right. I think the scaling of the picture is not quite right. I gotta fix that. But this is also quite interesting. This is a completely different thing. This is I don't know much about rocket physics, but I made this small sandbox where you can, there are like different missions getting more and more complicated, so that it's like more testing this kind of making a digital experiment that opens up and sort of allows more functionality to be available. This is free play, so you can see that there's an animation that looks kind of neat. So this is a rocket being launched, and I can change the thrust and the mass and how much rocket fuel it has, and it has even 3 stages. So you see this is not very successful. It's coming down quite fast. So I should probably try again, pause, and then maybe reduce the pitch a bit, and increase the amount of maybe this here. Oh, that won't work. Oh. So I can also choose to set off from start from the moon, where the gravity is weaker, or Mars, Venus, Mercury, and Titan. So it's just to show the kind of ways that you can adapt these and expand these to become also more engaging and active and entertaining. This is something different. This is a quantum Hall effect in a graphene Hall bar, where right now the mobility is pretty low, so we can start by increasing that, and which is going to visualize what the longitudinal conductivity will look like on a log plot. You can also look at rho XX. So let me just do this. And if I then also reduce the temperature, so now it's the room temperature down to 1 Kelvin, I'll get the familiar Landau fan coming out here. And there's a lot of parameters I can select, and the maybe familiar plot of Hall plateaus and Shubnikov-de-Haas oscillations becomes apparent when I sort of remove this sort of line cut in towards the center. So this is a quite powerful way of making a simple physics model come alive and to be able to interact with a simulated device in a way that makes sense in terms of comparisons with experiment. This is something I also don't know much about. This is a wind turbine, something I cooked up really quickly. And here also there's a sort of staged approach where you can have different stages that becomes more and more sophisticated. I'm not going to demonstrate it here, but one of the things that I found interesting is to see for myself like how things like the dimensions of the rotor, also the height of the rotor, in a later stage I can unlock that, but how that affects the power that is generated by the windmill. Yeah, so this is something that I do. This is visualizing van der Waals forces, where you, instead of having a simple chemical bond signified by an individual stripe, any atom in one graphene layer down here will interact with any atom in the other layer. So these multiple stripes are sort of indicating that. I can kind of switch on more of these, and you can see that if we slide the layers to the side like that, you can see that these sort of bonds become weaker and detach like elastic springs. This is a visualization that shows how the van der Waals forces act between two graphene sheets. This is also another quite useful little simulations. This is a kinetic Monte Carlo simulation that simulates how electrons are being scattered down through a substrate. As far as I know, I used all the right theory to do that, or the right equation and scattering cross section and so on. There's still some problems with the accuracy, so that I haven't gotten the depth quite right. But qualitatively, this is a very accurate representation of what you would get with commercial simulation software. And the speed it runs with in the browser with HTML and JavaScript is quite useful. So this is means that the time it takes until the student can interact with a Monte Carlo simulation like this is fairly short. I'm still working on the quantitative agreement with reality. There we have something like this. It's also related to electron beam lithography, where this is illustrating the proximity effect. So I can change the backscattering range. That's sort of the scattering effects that we just saw in the simulation before going on in the substrate. And this leads to some dose outside the lattice I'm trying to expose here. So you see there's some residual dose outside these regions, which is related to what we call proximity effect. And depending on the range of these, you can see that that effect, if we can increase the backscatter range, then we are reducing the problems with the distortion of the patterns on the short range. This is also something that is quite helpful. Another thing related to e-beam lithography is this sort of simulator that shows how you have sequential shots of electrons in a grid that will eventually draw a specific pattern. That's how electron beam patterns are being drawn. And you can see that depending on the shot size, sort of the distance between each of these electron shots, you'll get different doses. Again, related to electron beam lithography, showing the aura field emission and what we call Schottky emission in electron guns, also relevant to transmission electron microscopy and scanning electron microscopy. Here you can see that depending on the work function and the temperature and the extraction voltage and the tip radius, these sort of cold field emission or Schottky emitter, which is like thermal or field enhanced thermal emission or thermiotic emission, how the emission current is varying depending on the Fermi distribution function, including the temperature and the work function here. Finally, of the examples I chose to show you, this is also pretty neat. This shows the two graphene sheets, 77, the unit cells and size. I can change that pretty easily. It updates really quickly, so you can see here what happens if I have smaller pieces here. So these sort of periodic lattices you see here are called moire lattices and are very important for some of the most interesting things that happens in condensed matter physics right now. But here the purpose is not so much the otherwise very neat visualizations of moire lattices, but it is to allow the students to understand how the total van der Waals interaction energy is calculated based on, or can be calculated based on the lattice positions and also the pair-pair interaction potential. So what you have down here is the van der Waals energy, and that actually compares very well with the reports on van der Waals or adhesion energy and also surface energy of graphene found experimentally. So this is something that the students can directly go in and calculate here. And what they also learn is the theory behind it. This is just a visualization that allows you to kind of get a real-time computation of those sums and integrals that we look at in class.